Welcome to our third video on the construction of stochastic integrals. All right. So what we have seen in the last video is how to construct the integral. So if we have constructed the integral from 0 to capital T of a function which was in H2 integrated against the Brownian motion B. And this was fine as long as f is in our space H2. Okay, so this is now was done for fixed terminal time, which was assumed to be a finite number. What we want to do now in this video is to understand how to get an integral process and first properties of this integral process. So we want now to consider this integral as a process in time. So we only integrate from 0 to small t, and then we want to consider this as a process running in time. Okay. So the difference now is, okay, we constructed it for a fixed time point, and now we want to have it for each time point between 0 and t. And this is the content of the next theorem, where we need to ensure that this is possible, and we have actually all the tools already available to do so. Okay, so what's the content? So for function in H2, there exists a continuous martingale. Let's call it X. Such that X is equal to our integral operator. So this was just I of f. If we integrate now a function, and we only know how to integrate from 0 to t, to capital T, so we multiply with the indicator function from 0 to small t. So basically, we set the integrand to be 0 after time little t. And this is what I understand as integral up to time 0 to little t. And this is p almost surely fall. Okay, so what we basically say here is, well, I have a stochastic process which is continuous in time. So the sample paths are continuous, and the process itself is a martingale, which is a modification of the E2 integral from 0 to little t. Okay, so basically you can always say we find a modification of the E2 integral, which is a continuous martingale. And this is what we consider then as the representative of our martingale in the following. Okay, how do we get this? First, we have to prove it. Proof. First thing we do is, okay, so we again like split it in several steps. And the first step is we consider the case where we have simple integrands. So f is in the step function, a simple function. Right, so simple case. So let us take a sequence of H0. So these are the functions. So Fn is a sequence of functions in the H2 space restricted to those which are simple. And we assume that these Fn's approximate F in H2. Right? And from the last video, we know for every f in H2, we can find a sequence of simple function which approximate it. Okay. And well, we have assumed, okay, we assume that we also have the representation of Fn, which is given, right, sum of f minus 1. So we sum from I to 0 to some m, some natural number m, which might depend on n minus 1, and then we have ani indicator function. Here we go. This is just to remind you how, I mean, what the typical representation of Fn is. Now we want to define the following process, which is xn. So xn is rather simple. Defined, it's just the integral of the function Fn. Well, this is simple. We know what this is. And now restricted to the interval 0 to little t. Okay. Yeah. So what do we see here? If, let's assume, then, okay, if we analyze this Fn process, what this turns out to be a continuous martingale. This is why. Well, let's look at the k in our index set 0 to m n minus 1, and such that t is between t n k and t n k plus 1. Okay. Okay. So how does my process look if I have such a t? So then my process is just a nk multiplied with the increment from t to t n k, and then all the sums which came before this time. Okay. So what we know from this, so this process is a continuous martingale. Is a continuous martingale. For all that. Right. Okay. So this might be a bit farce, but this is really not hard to check, right? It's a continuous because the Brownian motion is continuous, and that is a martingale because these here are FTI measurable, and the Brownian motion is a martingale. So check yourself. Okay. Okay, and furthermore, we have Dup's maximal inequality because towards we have here martingale. So Dup's maximal inequality tells us, well, for all n and m in the natural numbers, and let's say n is by convention bigger than m, and every epsilon bigger than 0, what do we have? That the probability that the running supremum between 0 and capital T of the difference of xn minus xnm, right? So the difference of two martingales is again a martingale. So this here is just a martingale, and the probability that this is bigger than epsilon is nothing, is less or equal than the epsilon to the power minus 2, and then the expected value of the terminal time, the power 2. Okay. 2. And well, for the terminal time, we have already constructed the Ito integral. So this is Ito's isometry, which tells us this is nothing else than epsilon to the power -2 and then Fn minus Fm in the H2 norm. And now we have here not normalized, so we have here a square. Okay. So that's the observation. So we found here, we constructed here a sequence of continuous martingales, and the x will be just the limit of this sequence martingales. Okay, and this is what we do in step 2, where we need to show that these xn are converging to a continuous limit. I mean, that's, yeah, this is step 2. They exist a subsequence as usual, so right, such that x and k converges to x on 0 to t p almost surely. And this is if k goes to infinity. And this here has to be a continuous process. Okay, so this is the claim I want to show in step 2. So let's do so. Okay, first thing I want to do in order to show that I have this converging subsequence, I want to choose my sequence of natural numbers, so nk. Right. So these are natural numbers. Such that if I look at the supremum for all n, right, of fn minus fnk, they are smaller than 2 to the power 3k. So I have, I know that these Fn are converging, so I just consider the standard trick. I consider a fast converging sequence, and this is how fast the subsequence should converge. Okay, I can always do this. That's nice. And this means for all k, okay, so k and n. What do we have? Well, so we go back to our inequality we have seen here, or derived here, and now we know that here's this fast converging sequence, so we just combine these two arguments. What did we get from this? Okay, we know that if we look at the probability that this running supremum of x, and now we take the subsequence k plus 1 t minus nk t, let's say, gets bigger than 2 to the power. So we choose the epsilon to be 2 to the power minus k. And then we know by the Dup's maximal inequality and isometry that this is can be estimated by 2 to the power 2k of the difference of f and k plus 1 minus f and k in the H2 norm. And here we see why I wanted to have a fast enough converging sequence. Right? We want that this goes to 0, and luckily this here is less than 3k to the 3 to the power minus 2 to the power minus 3k. So this still goes to 0. And now Borel-Cantelli, Cantelli's lemma tells us, well, they exist. Oh, let's say this is they exist 0 with probability 1. such that the random variable c bigger than 0, such that this here, the difference in the supremum norm of k plus nt minus kt is less than 2k for all k being bigger than c on this event of measure 0. Okay. This is the usual trick how you go from a sequence which is converges in probability to a almost sure converging sequence by choosing a fast enough subsequence. And this is an argument you might have seen already. Okay. And this means, well, if I look at this fast converging sequence and I put an omega, this is a k. So this here is for every omega in omega 0 is a Cauchy sequence. Well, Cauchy sequence in the space C to T and the supremum norm. So what we know is that the limit which exists, so exists a limit x0 on this and outside, well, outside this set, we just say x is identical to 0 on the complement of this one set. Right? I mean, we have a complete filtration or a complete probability space. So outside outside the set 1, we can do whatever we want to. Okay. Okay, so we have now shown, we have shown that, well, there exists such a process x, which is continuous, on basically at this property, but we will check this later. The first, as a third step, second last step, we want to check that this process we got out is indeed a martingale. Is a martingale. Okay. Well, okay, x is adapted. The first thing is x is adapted. Adapted, right? I mean, this is not a problem because, again, we have here complete filtration. So since as f is complete, that's not an issue. So the only thing, the main thing we need to show is the martingale property. And the integrability. Okay. So note. Let me consider the difference xt. Okay, right? So let me approximate. I want to show that this sequence of x and k, so this fast converging substring, also converges in L2. So then I get the integrability. So let's apply phi2, which allows me to pull out a limit L to infinity of an L. Right, so I approximate this process x with another, with the same sequence, subsequence of x. Then I have here the difference between x at of n L and minus x at n k in the L2 norm. And here the good thing is I can use Ito's isometry. Right, so I can, well, here I know that the limit exists, so I can swap from the limit inferior to the limit. Doesn't matter. And then I have here by Ito's isometry just f and L minus f and k in H2 for 2. And well, here, I mean, I know that the limit exists, so this is nothing else than f at k in H2. So this is the first limit. And now I'm sending k to infinity as well, so this goes to 0. Right? In particular, x is an L2, right? So, but in particular, this means that you can also leave it away because the L2 space, the LP spaces are ordered if we talk about probability measures, or finite measures in general. Okay, cool. Okay, so last thing we want to check is the Martingale property. So let us consider an S, T, right? They are ordered, and I take an F, which is an A, which is F as measurable, and K is, okay, it doesn't matter. Right. Okay. Okay. And K is natural number. Okay. So what we want to show is that if we look at the difference of xt minus xs multiplied with the indicator function of A, and A is fs measurable, so this has to be 0. Okay. So how do I see this? Well, I sneak in my approximating sequence. So this is the argument as before. I mean, we have also seen before. So here, let's sneak in my approximating sequence of fnk. Okay, now I sneak in, so I have to get rid of it again. So what do I get next? K t minus fn st. Okay, and what last term I missed is absolute value of the expected value of fsn minus x s minus x and k s. Oh, here we go. T. Okay. First thing we observe is this is just 0 because S and K is a martingale. Right? This was step 1. Cool. So let us further estimate this. So this is can be estimated by Jensen's inequality. Jensen's by getting here Sn squared T. And here let's use Jensen's again. So what we get here is that here we are. Sn minus Snk. So this is just from the second term here. Okay. But this is what we understand, right? Because this is nothing else than 2 times, I mean, it can be estimated 2 times the f minus f and k in the H2 norm. And this goes to 0 as k goes to infinity. Right. So we know that This is the process X is a martingale. Okay. All right, last step is that we have to check that this process X is indeed a modification. So we want to show what I have that xk at x at time t is nothing else than the integral operator of f multiplied with the indicator function of 0 to small t. For t and t. Okay. Well, again, we rely on our sequence. So what we have is we have f and k. I mean, this is how we constructed this. Is given by f, the integral operator applied to f and k, indicator of 0 to t. And we have that the f and k indicator 0 to t also goes in L2 to ft, or this has to be in ht. There to t. And the last thing we know is that this here go to in L2 to xt. Of course, all if k goes to infinity. So this we immediately get that xt is equal to ft. There's actually not much. I mean, this is by construction how we set everything up. So this holds almost surely. Cool. So what we see here is, okay, we can always find a modification of the equivalence operator, which is a continuous martingale. And this is what we make now to definition of the E2 integral or E2 integral process. So for f in H2, the E2 integral or E2 integral process right, is defined by, so this is our integral process here, which is f s dbs, right? This is nothing else than the process x, which we just have introduced, and this is almost surely nothing else than a modification of the E2 integral operator of f restricted to 0 to t. Cool. And just to remind you, so this process x is just, I mean, so we just say, okay, if we want to talk about the E2 integral, we always choose the continuous martingale, which is in principle is a modification of the actual E2 integral. So we can always think of, if you leave this is a continuous martingale if your function is in H2 is given in the last theorem. So this is theorem 3.7. Okay. So let me conclude with two properties which are rather central. First one is given in remark 3.9, and this tells you the stochastic integral here to TF SDBS is a linear operator, right? I mean, this is how we constructed it. So just remark you on H2. right? And why? Well, because it is a linear operator on h to 0. So this just extends. Okay. And the last property, which is left for you as an exercise to prove, this is 3.10, is telling you, okay, the E2 integral behaves rather natural on the stopping times. So what does it mean? So let f be a function f2, and mu here is a stopping time. Be a stopping time such that the function f multiplied with the indicator function of 0 to mu, nu is 0. Then the integral process. So what do we have here is, then if we look at the integral from 0 to t, TBS is on the multiplier outside with the indicator function of nu. This is equal to 0. Okay. So what is basically this theory or proposition is telling you is, okay, it doesn't matter if you stop the integrand or the integral itself. So you can always move it out. So this is what's left for you as a homework to prove. So see problem sheets. All right. So we are done with the construction of the E2 integral, or respectively the E2 integral process. In the next videos, we will then talk about how we can generalize the class of integrands from H2 to something even bigger, because we will see that natural integrands are still not in this class of H2. Thank you for watching the video.